rover and it's landing this week. And so that's how I got in contact with Judith, and she was able to organize this talk very quickly with me. Solar System Ambassadors Program is a volunteer program of which I'm a member. It's a NASA program managed by the Jet Propulsion Laboratory, JPL, at the California Institute of Technology. And I'm a NASA volunteer. And I've been speaking for some time now on the subject of Mars. Usually my talk is a little bit broader and is about whether or not it's possible to live on Mars. And I'm here addressing a fourth grade group. And I think they get a charge out of me because I tell them one of them is going to go to Mars, right? It's not my generation. We're way past it, but sometime hopefully in the mid-2030s, maybe one of them is going to be helping build a rocket or get on a rocket and go to Mars. And as Judith was kind enough to mention in the introduction, this is really a bit of a precursor to the landing of the latest rover, originally known as the Mars 2020 rover, and then later named as part of a contest as Perseverance, which is due to land Thursday. The NASA live coverage begins, as you can see here, although it's probably going to be about an hour and a half hour later before the actual touchdown is expected to occur. Rather than assume you know a lot about Mars or a lot about astronomy, and I appreciate probably some of you are space enthusiasts, I thought, well, let me try and give some background. And this is the same kind of background that I try to give as an introduction when I talk about whether or not we can live on Mars. And I usually show this picture, which I like to show because this is something that really wasn't well understood when I was young and as a student, what the Milky Way might have looked like from outside. We thought it was what was called a grand design spiral. We now realize that the Milky Way is actually something called a barred spiral with that large, bright central bar across the middle. And our sun is kind of halfway out, sort of in the suburbs on the edge of one of those spiral arms. And it really is one of those little points of light that you can't resolve easily here in this picture. But on close-up, we know our sun is that great big gaseous ball in the sky that's bright and gives us light and heat and warmth. And I show this picture of the solar system, and I say it's the planets are here kind of, because this is not really to scale. This kind of shows the planets in the correct order from the sun, but they're certainly not in the right scale distances. If we tried to do that, it would be very difficult to do it on a single slide. But what I'd like to show you here is the fact that starting from the sun, we have four what are sometimes known as the terrestrial planets, Earth being the third, and then Mars being the fourth. And so you can get some idea of where the Earth is compared to Mars, and the next thing out is the asteroid belt, and then we start getting to the gas giants, Jupiter, Saturn, Uranus, Neptune. The reality is Mars is about 1.5 times further from the sun than the Earth is. And that distance, roughly 93 million miles, is known as an astronomical unit, AU for short. So the Earth is roughly 1 AU from the sun, and that means that Mars is about 1.5 AU's distance from the sun, or about 142 million miles on a very sort of average orbit. Okay, so a little bit more about what Mars is, and a couple of photos of two different sides of Mars there on the right. As I mentioned, it's a terrestrial or rocky planet. It's the fourth and the last one out. Again, orbits further away from the Earth. There is ice on Mars, and you can see some of the polar ice caps there in the photo. There is both water ice, but there's much more dry ice or frozen carbon dioxide on the planet Mars. There appears to be liquid water on Mars, but it's not on the surface. The conditions on Mars are not such that liquid water exists anymore on the surface. It's simply too cold and too dry there for water to exist on the surface in liquid form. Mars is tilted, unlike the way the photographs are shown here. So it does have seasons like the Earth does, and those polar caps will become enlarged when the northern hemisphere, for instance, is in winter, and shrink when it's in summer, like the Earth does. A Martian day, interestingly and really coincidentally, is roughly the same length as an Earth day. It's a little bit longer by about a half an hour. Sometimes you will see that Martian days are referred to as sols to distinguish them from Earth days, but a Martian day is about 24 hours and 37 minutes. A Martian year, as you might imagine, Mars being further away from the sun, is significantly longer than an Earth year. And in fact, it's about twice the length of an Earth year. It is a very cold place, largely because of its distance from the sun and the fact that it's that much further away from the sun than the Earth is. But it's also very dry, and the fact that it doesn't have much of an atmosphere to trap in heat is another reason why it's both cold and dry. If we were to try and think about the sizes of Mars compared to the Earth, and maybe showing the moon in also as a nice comparison, Mars is roughly half the size of the Earth, and our moon is again about half the size of Mars. So give you an idea of what the size of the planet is, kind of midway between the Earth and the size of our moon. Yeah, Mars is a number of things. I mentioned very far away. So at its closest approach to the Earth, it's about 40 million miles away. Since the moon is only 250,000 miles away, that means that Mars is 160 times further away than our moon. So if you think getting to the moon is a big deal, getting to Mars is 160 times that big a deal. And it's not easy to get there with a successful mission. The overall rate from all of the people who have tried it, countries who have tried it, is only about a 40% success rate. So it's not easy to do. It's not easy to get there safely and have a successful mission. Mars is very cold, 81 degrees Fahrenheit, not an unusual average temperature. I looked yesterday at the Mars weather, and I think the overnight low was 99 degrees below 0 Fahrenheit, and the high of the day was just around freezing, or 0 degrees Fahrenheit, probably right near the equator. I mentioned this before, but it's an important fact, and it's going to come up again when we talk in some more detail about the rover, just how dry the Martian both surface and the atmosphere is. No more liquid water, but there's certainly plenty of evidence, and in fact, we're going to look at some of that, at least visual evidence, that Mars was once indeed a water world. It doesn't have much of an atmosphere around it. So unlike our atmosphere around the Earth, which is very thick and rich and heavy and contains a lot of oxygen, which is how we developed the way we have, the Martian atmosphere is very thin. It's less than 1% of the Earth's atmosphere. So you would have to go to maybe an elevation above the Earth at 40 or 50,000 feet, where you typically couldn't breathe, to find the density of an atmosphere as low as it is on Mars. And again, even if you could get something like that at 40 or 50 feet above the Earth, at least what you would get there would contain oxygen. That's not the case for the atmosphere on Mars, as you probably know if you've read anything about it or know anything about it. The little atmosphere that there is, the very thin atmosphere, is mostly carbon dioxide, and so it's not the kind of air we think of that's got roughly 21% oxygen in it. Another important fact about Mars is that it doesn't have a protective magnetosphere. So the Earth has a protective envelope around it that helps prevent the most dangerous kinds of rays and radiation from reaching the Earth. Mars has no such protective shield around it, so it's a more dangerous place with regard to the radiation from the sun as well as outer space Even though it's further away than the sun, it's even more dangerous place from the sun's dangerous radiation because it lacks the protective magnetosphere. You may have heard of the Van Allen radiation belts. That was the first understanding of this magnetosphere around the Earth and what protects us. It looks a bit like the lines around a magnet. And of course, the particles come in around the poles, which is what gives us the effect of the aurora, either at the north or the south pole, is these charged particles getting in around the magnetosphere. Okay, those are the slides I had with the sort of brief introduction to Mars. But I thought that before I began talking about the rover and about the Perseverance rover, that this might be a good opportunity to stop briefly and find out if we have any questions. Judith, are you still there? Are you in a position to unmute people if there are questions, or chat them through if people chat you the questions? Just see, would I see a chat bar here if I were looking? Don't know if I would or not. Okay, I'm going to continue on then. Again, if there's questions, you can certainly ask them at the end of the talk. I like this photograph of the rover because we see one of the techs there standing, and you get an idea of the size of the rover. It weighs about a ton, and you can see it's a six-wheeled vehicle. It opposite the technician there, you can see a kind of a folded robotic arm in the front. We'll go on to talk about some of the pieces on the rover, but I thought that was a nice photo because it gives you an idea of the scale of the size of it. Some quick facts, and there's lots of information on the NASA websites. I'll share those links at the end of my presentation. The NASA facts, you can see there's one on Mars 2020, which was the name and remains the name of the overall mission, even though the rover has been named Perseverance. As you can see, the main job is all about seeking signs of ancient life and collecting rock and soil samples. It launched this summer, July 30th, from Cape Canaveral here in Florida, and the landing will be on Thursday around early afternoon. The landing site, and we'll talk a little bit more about the landing site and why that was chosen, a place called Jezero Crater. The mission duration is at least one Mars year, or somewhere a little over 2 Earth years. And the very interesting tech demo, and again, I'll share some information about that, which is what's called the Mars helicopter. And so, you know, we tend to get lost, at least easy for me to get lost in the great pictures that we've got back from Mars in the past. Particularly, I like the 3D pictures that you can put on a pair of green, red 3D glasses and look at and get a feel for what it's like to stand on the Martian surface. But in reality, this is a complicated science experiment or package of science experiments, and there's 4 science objectives. And these kind of follow the pattern previously with NASA, which is basically to try and follow signs of water, right? So we're looking for habitability, whether there was an opportunity there to support microbial life, whether or not we can find what are sometimes referred to as biosignatures, or evidence that there was microbial life in those environments, particularly with regard to special kinds of rocks or clays. This mission will be the first on Mars to actually cache samples, meaning that there's going to be some rock and soil, actually better known as regolith samples, that are going to be stored in small vials, and they'll be waiting there for us to collect them again in the future, hopefully as part of some manned mission. And again, we could talk a little bit about that, but the basic idea for caching the samples is so that once they're stored, they're no longer subject to contamination, whether it be from our probes or whether it be from future visits by astronauts. There's also another great technology demonstration on board that we'll talk about, which is the idea of taking in that carbon dioxide from the Martian atmosphere and making oxygen from it. And this is kind of a little more interesting, focused on some engineering aspects of the project. And you can see kind of 5 cool things. One is some newly designed wheels, and I'll show you in the next slide why they had wanted to redesign the wheels after the Mars Curiosity rover. This will also be the first rover that will have a microphone on it, so that we'll actually be able to hear the sounds on Mars, which will, I think, be quite exciting to be able to both hear and see photographs at some stage. I mentioned this idea of collecting cool rocks or regolith samples and then being able to store them until a future date where we can collect them. And again, we'll talk more about this idea of getting oxygen out of the thin, well, it isn't really air there on Mars, it's a thin atmosphere of carbon dioxide. Right, so I saw this photograph, and somewhere else I saw this description of rocks versus the stone cold aluminum wheels. And I thought, yeah, that's helpful as a reminder that not only do these wheels need to go over some rocky terrain to go from one place to another, but those aluminum wheels are actually extremely cold, right? 81 degrees Fahrenheit is going to be an average kind of temperature on Mars, and maybe it'll heat up to 0 degrees Fahrenheit, but by and large, it's going to be very cold, and therefore I'm sure the cold led to some of the fragility of the aluminum wheels here that you could see having busted through. Right, a little bit about how we got there, which unless you're involved in physics or you're involved in space program things is not at all obvious. I'll sort of begin at the bottom. I don't know if I could pick up a cursor at the bottom left-hand part of the screen here, where the Earth was at launch and where Mars was at launch back at July 30th when the rover was launched. And you could see the white line, which is the rover trajectory, and you can see the interception of Mars here. Again, because Earth is on a smaller orbit, we've moved further away from Mars since when it was launched. And in fact, the closest approach between Earth and Mars, actually is known as opposition, actually occurred around October 13th of this year. And that was, generally speaking, the best time for amateur astronomers, people like me, to get out their telescopes and see whether or not we could see any of the features on Mars. Now, could we have got there quicker than the roughly 6 months it's taken us? The answer is yes, but then you have to expend energy slowing down at the other end. So this trajectory that's shown here is the one that uses the least amount of energy and therefore the least amount of fuel. The idea is that we don't have to waste energy, at least not in space orbit, slowing down to get to Mars. We'll have the right speed when we get there to enter into the Martian atmosphere. Now, of course, once we get into the Martian atmosphere, we're still going to have to slow down, but we won't be slowing down in orbit to get there. Okay, and where is it again we're going? Right, a place called Jezero Crater. Jezero in a number of Eastern European languages means lake, and we'll see in a minute why that was chosen as the name. You could see on this map, which is the planet Mars kind of straightened out in almost like a Mercator, projection map like we might see of the Earth, a rectangular map. And you could see Mars just on the border of a large dark feature. That dark feature is known as Syrtis Major. It's one of the few features, Martian features, besides the polar caps that you can see from a backyard telescope. And we'll talk a little bit about why Jezero crater might be an interesting place. And I'll draw your attention here to this feature in the middle. And to those of you who might have some experience in looking at aerial photographs or might have some understanding of geology, this area here sure looks like it might have been some kind of river delta, and that there might have been flowing liquid coming down and spreading out here onto the crater. And so the thought is that if we're going to look for signs of life, that one of the great places to look would be a place that looked like it was previously a river delta. So we would expect something like this to be much richer in terms of potential targets for finding evidence of life. Okay, what's going to go on? Whoops, excuse me. What will go on Thursday is a number of different technologies. A couple of them are different than they were with Curiosity. The basic overview, though, is that it will use a combination of a parachute and then some retro rockets when you get closer. So you'll see that there's a guided atmospheric entry and a guided entry, and then the parachutes will deploy. These are very large parachutes, but because the Martian atmosphere is so thin, the parachutes aren't capable of slowing it down enough on their own. In fact, the parachutes will only slow down the craft to about 200 miles an hour. So it'll take it from going at about 1,000 miles an hour up in here to about 200 miles an hour at its slowest after the parachutes are deployed. There is some new equipment involving how the parachute is deployed. Previously, it was deployed automatically. Now there's a trigger mechanism that I'll talk about that is designed to choose to deploy the parachute hopefully closer to the landing site. So that's one of the new technologies that we'll talk about. And then the second one is this terrain reactive navigation solution. This one is more about avoiding hazards near the landing. And this is also different than Curiosity. So the trigger on the parachutes is different, and this active range finding is different. Hopefully this is going to let the rover land much closer to where it's supposed to. It uses that same sky crane technology, it's called, that had been used before in Curiosity, where the retro rockets will fire and then the rover will be dropped to the surface. We could come back to that later if there's questions at the end, but that's basically the sequence that we're going to see take place. And the range trigger, this is the deployment of the parachute, is designed to make a narrower target of where the rover will land, right? So this is actually a comparison using the Curiosity landing site as an example of, with the trigger, how much of a smaller target area you get than without the trigger. So again, the idea of the range trigger on the parachute is to help do a better job of landing accurately and close to the landing site, whereas the active navigation system is more about avoiding hazards. And so you can see here in this little animation that the landing technique involves taking descent photos, comparing it with an onboard computer to an orbital map, and then diverting the rover if necessary so that it lands on flat ground and not on the side of a mountain or on a giant rock, etc. Now, the reason why this all needs to be built into the computer that's on board is that you cannot operate the vehicle with a joystick from the Earth. Where Mars is now, it takes roughly 11 minutes for a signal to go from either the Earth to Mars or back again. So you clearly can't steer it when you've got 22 minutes worth of round trip on the signal. And so one of the things that's complex about designing the landing and designing how the rover moves around is that it's got to be pre-programmed in. And if it's not pre-programmed in before takeoff, then it's pre-programmed in while the rover is on the surface and is kind of deciding where it's going to go. And so here's a different view of that river delta area that we saw on the edge of the Jezero crater, and the green line shows a possible path as an example of where the rover might go. The what happens is that overnight the rover stops. The people on the ground program it in for the next day. Again, all to avoid the fact that you really don't have joystick control when you've got that long a round trip for the signal. What happens with the people who program it, though, which I think is pretty interesting, is that they use 3D glasses to and the cameras on the rover to look around and figure out where they're going to make the rover drive to and avoid hazards, things like that. There's a nice looking rendition of the rover with that robotic arm in the front deployed. I think I mentioned the rover itself weighs about a ton. That head on the robotic arm, which is about a 7-foot arm reaching out there, is about 100 pounds worth of equipment there on the head. And these are some of the scientific instruments. And I'm going to manage to touch on all of them, but not discuss all of them in detail, because I think it would it might get a little bit tedious. But we're going to talk about hopefully some interesting aspects of the different instrument package that's on the Perseverance rover. I'll mention where possible where some of the differences are with Curiosity. I'll draw your attention, since I've mentioned it a couple of times, at the bottom of the screen to something called MOXIE. That's the demonstration unit that's going to take oxygen from the Martian CO2 atmosphere and hopefully collect it. Another new feature, this didn't exist in Curiosity, another new feature is something called RIMFAX, which is a subsurface radar, which will allow the rover to look down underneath the surface of Mars, hopefully looking to see whether there's water deposits or other kinds of deposits it can see. As you might imagine, I think there's 19 different cameras altogether of different kinds on the rover itself. And we'll talk about this. There's also a couple different kinds of spectrometers. This one's an ultraviolet spectrometer. This one's an X-ray spectrometer. There's also a visible light spectrometer up here in SpectroCam. And there's also a more sophisticated weather station on this rover than there had been on Curiosity. So there's a few features that are going to make Perseverance different than Curiosity and allow it to do some different things. Mastcam Z, okay, right there near the top. Advanced camera system, stereoscopic imaging capabilities. It'll have two lenses that are 9 inches apart, so that'll allow us for some pretty good stereo vision and 3D vision. The ability to zoom to help pick out the best rocks, and that's going to help for hunt places for signs of life, looking for water signs. So if you like the part of the eyes of the rover. SuperCam's a little bit more complicated than that in that it's going to examine rocks and soils with a camera, which can look close in. It's also got a laser in it that can burn off the top layers of dust or the top layers of a rock to maybe see what might be from underneath it. And I'll talk a little bit about how spectrometers work. The great thing is it can do science from afar. I think the range on the laser is about 20 feet. Hopefully it's going to find great rocks and, again, look for areas where life might be preserved, or at least evidence of life might be preserved. Also, it has the ability to measure hazards from the dust. One of the things that the rover will do is to hopefully do a better job of understanding how dangerous the Martian dust might be were we to send some kind of a manned mission there. And it says measures the air, but we know it's not really air. It's a very thin carbon dioxide atmosphere. Okay, so signs of life. What do we mean when we talk about biosignatures? And here I quote Sarah Stewart Johnson, planetary scientist, saying Mars was potentially habitable, but there's still this big question of whether life ever did take hold there, and if it did, is it still there? And the reason why the scientists feel that it was habitable was because it appears there was a time when there was flowing water. It may have been very salty water, but there appears to have been a time when there was flowing water on the surface of Mars. And a little bit more specifically, what is meant by trying to look for signs of life? Well, an example are kinds of clays called smectites that can contain records of complex organic compounds. And organic compounds in this context does not mean that they were part of plants that were grown without resorting to pesticides. But organic compounds here in the chemistry sense, meaning that they contain carbon. We're carbon-based life forms, and so as near as we can understand life, carbon's necessary for life. Life tends to be clumpy, and so if we find layers rich in these organic compounds sandwiched in between organic poor layers, that will be a very strong indication that maybe that represented living things at one stage. This is another a great quote from Professor Johnson, that they're still having huge debate over what qualifies as signs of life when you push back into the rock record that far. And so when we say push back that far, what do we mean? Well, you know, the Earth is about 4.7 billion years old. Mars may be a little bit older than that, but it appears as though the time when water was flowing on the surface was about 3.8 billion years ago. And there's different ways of expressing 3.8 billion years. I also used giga years or used scientific notation. That's a very long time ago. And so, you know, we don't really expect to find, for instance, live bacteria there. We think what we're going to find is the chemical signatures that bacteria was once there. What happens with a spectrophotometer or spectrometers in general is that they take light source. You could think of a prism, although typically the light is separated by wavelength with something called a grating, very narrow differentiation in lines. And in this particular example, you're taking the light of different wavelengths and passing it through some kind of solution, and then looking to see whether or not the light is absorbed at that wavelength or not. Now, we can also gather information like this without having the sample solution in here, but just by looking at different kinds of light sources. So for instance, what we know about stars is from looking at the stars themselves and splitting out their light and understanding, again, without the sample here, you know, where are the lines? What kind of wavelengths are in the light from different stars? And so when we talk about spectrophotometers or spectrometers on the craft, that's what we're talking about. And again, I don't like to assume that people would necessarily have an appreciation for this, but you know, what we think of as light is actually a small part of what's known as the electromagnetic spectrum. And it's this very thin band in here that kind of separates into the light that we perceive as visible light. So the blues are the long wavelengths going into ultraviolet. Blues are the short wavelengths going into ultraviolet. Reds are the long wavelengths going into infrared. There's long wavelengths there, short wavelengths here. You know, once you go a little bit past blue, again, you get energetic rays, ultraviolet rays, short wavelength, a lot of energy. Think of sunburns and UV light. And then a little further on, you get into X-rays. And so what happens is if you're trying to do chemical analysis using spectrometers, you can learn different things by looking in the visible spectrum than looking in the UV spectrum or looking in the X-ray spectrum. And so the reason why the rover is equipped with these different kinds of spectrometers is that there's opportunities to do more complex chemical analysis by looking at the light in those different spectrums. Okay, I like this one a lot, MOXIE, maybe because I'm a chemical engineer by education, but the idea of making oxygen from the CO2 in the Martian atmosphere is pretty cool, because it also kind of envisions a time when hopefully we'll be visiting Mars. And so perhaps what we will need to do firsthand is to put some units there that'll help make oxygen. And so the basic idea of MOXIE is it's a demonstration unit. It splits oxygen, O2, from carbon dioxide, CO2 by electrolysis. Some of you may have split water by electrolysis in high school or in college, and split water into hydrogen and oxygen. Similar kinds of thing here. Another way of looking at it is to think about it as almost like the opposite of how a car battery runs. So instead of getting the energy, we're putting the energy in and doing the separation. It's designed to be able to make 99.6% purity oxygen, and that could be used for future missions, either for breathing or for fuel, because liquid oxygen is a great rocket fuel. A couple of the other equipment suites that are on the rover that I didn't talk of in detail, but just mentioned: MEDA, Mars Environmental Dynamics Analyzer. That's the weather station. And not only will it study the environment, but hopefully it'll help us predict the weather, get a better understanding of the radiation, and also it'll show the correlation between the weather and, if any, and how the other instruments perform, which could be very important again for future missions. RIMFAX, the RIMFAX is not an acronym. It's actually named after a horse in Norse mythology. And the RIMFAX will help look underground via radar, hopefully detect water and ice like radars on Earth. And again, it'll be the first for Mars, and hopefully it'll give us some structural details and understanding of what's going on below the surface of Mars. Another cool thing that's going to be on this mission, something called Ingenuity, the Mars helicopter, although maybe calling it a drone would be a little bit more accurate. This is a nice photo because it shows the size of the Mars helicopter or drone in comparison to the size of the Perseverance rover in the background. You could see it weighs about 4 pounds. It's solar powered and recharges on its own. Got a wireless communication system, got 2 sets of rotating blades there, and it's got computer navigation sensor and 2 cameras all built into it. It'll have short flights. It'll only be 1.5 minutes or so, but it can fly up to about 160 feet away. Now, a lot of people have asked, you know, how do you make a helicopter fly or a drone fly in an atmosphere that's there where there's only 1% of the Earth's atmosphere? And I watched an interview with the chief engineer of this project, and someone asked him, he said, did anyone ever mention to you that it might be a bad idea to try and have a helicopter on a planet where the atmosphere is only 1% as thick as ours? And he responded, everybody, all the time. So they were aware that this was an engineering challenge, and hopefully they designed it in the right kinds of environments and vacuum chambers so that it'll work properly, and we'll get back some great drone photos of Mars. Right, well, just reminding everybody again, the NASA TV broadcast will go live around 1:15 Central Standard Time, although probably the touchdown is going to happen closer to 2 or 2:30. But if you want to watch all the pregame show and watch some of the demonstrations and animations, I think, again, if you're somebody who enjoys this sort of thing, you'll enjoy it a lot. There's lots of great web resources. I always start with the NASA ones. Their NASA TV, of course, where you would go to watch it live, or you could get it on your streaming device, maybe on your TV. There's a Mars 2020 website, which is great. There's also a bigger and broader Mars Red Planet website, which is also fantastic for more background information about Mars. And when I thought about background information, I found two pretty good background articles. One was in National Geographic around July when it launched about Perseverance, and the other one from Smithsonian Magazine, and both of those are available online. And I've sent Judith Wright this list. One of the other things that I share with people, particularly when I do library talks, and I often do a bigger library talk having to do with whether or not we can live on Mars, is that I share some of the books that I've read and that I found pretty good about Mars and how we'd get there and some of the challenges. And here's a selection here. Packing for Mars, if any of you have read any of Mary Roach's stuff, not only is it insightful and got a lot of facts, but it's got a lot of funny bits and pretty witty as well. And the Buzz Aldrin one, I think, is kind of great for young adults. Really a kind of a nice introduction to Mars that hopefully gets some young people enthused about it and fired up over it. Okay, so before I flip over into Q&A mode, I will thank you for your attention today. It seems like I took about 45 minutes for the talking part, so hopefully I'll get some good questions, maybe even some that I can answer. Again, I'm a volunteer because I think STEM is important. I mentioned already that I'm a chemical engineer by education. I don't think it's a stretch to say that one of the reasons I'm an engineer is because of my enthusiasm for the space program when I was a very young person. And so I hope I can transmit some of that enthusiasm to the young people when I go to talk to school groups. I've given you my email address there. Again, happy to talk. This is a volunteer program, so it's free of charge. Library, schools, other groups, astronomy clubs, of which I was a member, still am a member of the one in New Jersey, even though I don't live there anymore. Spent a few years as its president. But I will take a deep breath there, and hopefully, if I haven't put Judith to sleep, she's there and she can help me facilitate some questions.
Yeah, we've actually got one in the chat already. It's from Heidi. She asked, what are the primary power sources for the rover when on the surface of Mars? Is it nuclear, solar, or chemical?
It's nuclear. It's something called, trying to remember the acronym now, thermoelectric isotopic generator, something like that, but it is nuclear. It's a small little nuke radioactive isotope that runs everything. Other than the Mars helicopter, which has got its own little power pack and will run off solar power.
So if y'all have any more questions, you can unmute yourself, or you can actually type them into the chat, and we'll be happy to answer them. We have another one. You mentioned only 40% of Mars missions have been successful. What are the main reasons others have failed?
Because it's hard. And I think, to put it sort of at its simplest level, you're trying to do something that's perhaps more than 100 million miles away. It's too far away for you to do anything in real time. You may have heard about or read about or even experienced in previous missions the 7 seconds of terror as they're all there waiting to get the signal back as to whether or not the rovers actually landed in one piece. It's an incredible number of steps that have to be pre-programmed in and have to all work at the same time. So in some cases, the injection into the Mars atmosphere didn't go right, and the vehicle was lost before it ever reached Mars. In some cases, it entered into the Martian atmosphere, but at the wrong angle, and it burned up or crashed and was lost. So there's a number of things that can go wrong, and I'd say largely it's because of the incredible complexity of all the technology that needs to work together.
We've got a couple more questions coming through the chat. So Andrea asked, what types of living buildings would we have on Mars?
Yeah, good question. And in fact, there's some designs out there about how we might be able to make a brick-like buildings using some kind of 3D printer that we would put on the surface of Mars that would take the Mars regolith and help essentially build building blocks with it. And part of the reason for that is, again, I referred earlier to the fact that Mars doesn't have a natural protection from solar radiation. And so if we're going to have people there for any length of time, it's going to be important for us to be able to shelter them in a way that is either going to be underground or that'll mimic being underground by being able to make something like bricks from the Martian surface material.
All right, so Deb asks, will some part of the rover end up coming back? If not, how will they evaluate the rocks collected?
Really good question. Right. So I think there's 41 sample tubes on the rover. So hopefully, if everything goes well, they'll fill 41 very small tubes with either pieces of rock or pieces of the Martian soil, more technically known as regolith. And it'll depend on a future manned mission to go and go back to the rover and pull those samples and stick them in their pockets and hopefully bring them back. Hopefully that one of that group of fourth graders that I address, or a group of fourth or fifth graders today, is going to be one of the people doing that in the future. I certainly hope so. I hope I get to be here and watch it and smile when they do it.
That's really awesome. We are part of the lunar and meteorite sample lending program. So when they send samples from the Johnson Space Center, it's really cool to think about the missions. I think it was Apollo. Most of the samples come from Apollo 16 and 17. So it's really neat to think about how they went all the way there to get them, and they came all the way back, and then here they are in the library.
Yeah, pretty exciting.
So we have another question from Andrea. I know it will probably be 100 to maybe even 200 years away, but what are your thoughts on terraforming?
Yeah, it's a good question. In fact, I have a couple of slides on the subject of terraforming in my other talk, because we went from a stage where we thought terraforming was a more realistic possibility. And part of that idea was that you could somehow or another liberate some of the trapped ice, both carbon dioxide and water ice in the Martian polar caps, and that would help envelop the planet with enough vapor to hopefully act as a greenhouse effect and help trap things inside. The latest, unfortunately, though, the latest technical reports on that seem to indicate that there really isn't enough to do that there really isn't enough material there. So we'd have to discover some big subsurface reservoirs of water to do it, and we'd have to find some way to liberate that water and make it part of the atmosphere. So in theory, it could be done, but there's no clear technology path anymore that we can see that, oh, we can do these 10 steps and perhaps create some kind of an atmosphere. It's much more complicated than that. And it would take more than a few hundred years to actually have the terraforming take hold. It would probably be on the order of thousands of years.
Awesome. Do we have any more questions coming through in the chat, or if anyone wants to unmute themselves? I'm not seeing any more. Kevin, I just want to say thank you for taking time out of your day and talking with us. We're really excited about Thursday's landing. The community of Homewood is really big into STEM and NASA. And so when we received the NASA at My Library grant a few years ago, it was a big deal to us, and we've really appreciated the connections and the opportunities through that grant. Oh, we have another question coming through. Do we have the rocket technology to actually send humans there yet?
I think, we're pretty close, largely thanks to Elon Musk, right? I mean, it's useful for us to remember that Elon Musk didn't fund and found SpaceX just to deliver payloads to the International Space Station. In this case, human payloads he's managed to do now as well. But really, he started SpaceX to be able to go to Mars, and not with the idea of just going there and planting a flag and doing some science and coming home, but with the idea of actually having a colony on Mars and making human beings more than a single planet species. So I think the rocket technology is there. It's not easy. It would be very expensive. I think the earliest likely date would be maybe sometime in the mid-2030s. I'm hoping that's not too optimistic, but maybe that's just because I want to be around to see it. But I think the technology's there, and you're going to see more and more demos, particularly from the SpaceX people, of some rockets. Now, again, will it all be one rocket going there like we went to the moon? Probably not. It'll probably involve multiple stages, maybe rockets going there, dropping off MOXIE type equipment to make liquid oxygen there so that we don't have to bring the liquid oxygen for the return voyage with us, et cetera, et cetera. So it's going to be a complex undertaking, probably involving sort of preparatory robotic trips to Mars first before we can actually get humans there and back.
Very fascinating. All right.
I have my NASA t-shirt on today, but sometimes I wear my Occupy Mars t-shirt if we're.
I should have worn my Space Force. My sister works for Space Force.
Very cool.
Yeah, she's definitely taught me a lot about it, even though she's not into the actual science field. She runs the public relations department for Space Force.
Cool.
So she stays very busy. Well, thank you so much again. For everyone still listening, we're going to make this recording available on our YouTube channel soon and social media platforms. We also have a talk tomorrow at 2 p.m. and we have another one on Wednesday at 1 p.m. So we hope y'all sign up for those. The Zoom information will be sent out to you right after you sign up, just like today. Again, Kevin, thank you so much for joining us. We really appreciate you taking the time and teaching us all about Mars and the landing rover.
Well, thank you, and thanks to all the people that attended, and some great questions there at the end. I really enjoyed it. So you're welcome, and thanks back at you.
Everyone, I hope you have a great day. Please stay safe. I know the weather conditions are worsening as we carry on through the day, so we hope you stay safe and warm. So take care, everyone. Thanks so much.
Bye now.